Okay, so now that we've defined projective space, we can take a function, a meromorphic function, and we can ask the following question. Can we make sense of expressions like f infinity? So, okay, so the answer is yes. Is yes. And so note that, so we have P1, right? And so this is the union of two charts. So this is like the usual copy of C. With coordinate Z. And this is the compactified let's say not the compactified, the copy of C containing infinity. So we have the point infinity up here, and this is the coordinate here is zeta, and then we have this relation between these two guys that zeta is 1 over z, or z is 1 over zeta. And so when zeta goes to 0, right, z goes to infinity. All right, so let's make a definition. So f of z is holomorphic at infinity if and only if, and this is by definition, the function g of zeta defined to be equal to f of 1 over zeta, so we're just plugging in f of z, is holomorphic at zeta is equal to 0. Okay, so in a neighborhood of, so meaning it has a power series. It has a okay, so it's not just complex differentiable, but it'll have a power series. Okay, and so let's make some notation. So the functions, right, we'll look at here, f from P1 to C, holomorphic, f is holomorphic at all points, so analytic at all points. Okay, so this is going to be denoted by, so what did I use? So we're going to use this notation. Okay, so this is a field of functions. Or not a field, it's a ring. Because you can't divide by 0. Well, I mean, that's another thing. Well, you can't divide by 0, so there's going to be functions which have zeros. So this is the ring of functions, okay, on P1, which are holomorphic. So I'm just saying that it's a ring. So let's consider an example. So if we let f of z be 1 over z squared. Okay, so this is a meromorphic function on C, but note that here g of zeta is f of 1 over zeta. So this is zeta squared, which is clearly analytic at zeta is equal to 0. So it has a power series at zeta is equal to 0. The power series is just zeta squared. So this is holomorphic at infinity. It's holomorphic at infinity. Okay, so we can plug in infinity, and it makes sense here. And the value is actually 0. Okay, so here's kind of something that's interesting. So lemma, and this is just a incarnation of Liouville's theorem. So the holomorphic functions on P1 is just C. So these are all constants. Proof. Okay, so let's let F here be from P1 to C. Okay? So it's clear that F, so restricted to C, is holomorphic. This is a function from C to C. So it is entire. So it's holomorphic at every point in C. Okay, so we have an entire function. And if f is holomorphic at infinity, then we apply the definition. So f of z is f of 1 over zeta, which is g of zeta, is holomorphic near zeta is equal to 0. Okay? So then this means g of zeta is bounded in a neighborhood of infinity, well, of 0, and this is okay. So this is bounded in a neighborhood of infinity. So this implies that f of z. So now, since it's bounded on everywhere, so f of z is a bounded entire function. And hence constant. Okay, so this is by Liouville's theorem.